In this video, I'll cover multi-label and multinomial classification. I'll introduce both topics, and then I'll step through a multi-class contingency matrix and the process of computing multi-class precision and recall. Finally, I'll talk about macro-averaging and micro-averaging. So for this module, we've restricted ourselves to binary classification scenarios where we're just deciding which of two classes a test instance belongs in. However, in many NLP classification tasks, there are more than two classes. For example, in sentiment analysis, you might have positive, negative, and neutral classes. In part of speech tagging, you can have tons of classes, and even with things like emotion detection, you can easily have 6 or more classes. When you're dealing with more than two classes, there are two different classification paradigms that can come into play. There's multi-label classification and multinomial classification. Multi-label classification just allows you to assign more than one label to each instance. Typically, it's done by creating separate binary classifiers for each class and then running each of these binary classifiers on the given test instance. Rather than saying that the one with the highest confidence is the single class label, each classifier makes its decision independently. So you could have one label or you could have many more. Multinomial classification, on the other hand, just means that you're selecting a label from among multiple possible labels. It's a generalization of binary or two-class classification. You can perform multinomial classification in the same way as the multi-class setup from the previous slide, but rather than assigning all predicted labels to a given instance, you just keep the label that is predicted with the highest confidence score. When we do multinomial classification, we can still create confusion matrices. However, they're a bit larger than the ones we saw previously since they have rows and columns for each class. Here's what a three-class confusion matrix would look like. Our diagonals, so cells A, E, and I, are cases where the predicted and actual labels were the same, whereas the other cells represent different types of misclassifications. For example, cell H contains the number of instances that were predicted to be class 3, but had actual labels of class 2. If we want to compute multi-class precision, we can do it more or less the same as before, but just factoring in the correct and incorrect predictions for additional classes. For example, if we want to compute precision for class 1 in the confusion matrix here, we divide the value in cell A, that's the number of true positives, by the sum of the values in cells A, B, and C, since those together are the total number of instances predicted to be in class 1. A multi-class recall works similarly. If we want to compute multi-class recall for class 1, we would divide the value in cell A, again the true positives, by the sum of the values in cells A, D, and G. These together are the total number of instances with actual labels of class 1. If we want to check a system's overall performance in multi-class classification settings, that is, we don't just want to know how well we're doing for a single class, but how well we're doing for all classes, we can combine our precision or recall scores in two different ways. We can macro average them by computing the precision or recall for each class and then averaging that score over all classes, or we can micro average them by collecting the true positives, false positives, etc. for all classes into a single contingency table and then computing precision or recall directly from that table. Here's how the first, macro averaging, would work given our multi-class confusion matrix. You can see that for each class, we could create a regular binary confusion matrix similar to what we saw previously. To do that for class 1, for example, we would set the true positives to A, the false positives to B plus C, and the false negatives to D plus G. True negatives aren't really well defined for this setup, but we also don't need them to compute precision or recall. We'd create the confusion matrix for classes 2 and 3 similarly, with the true positives being set to cells E and I respectively. Then we'd compute our metric, so precision for example, for each class using the regular two-class formula. We'd end up with 3 separate precisions in this example, one for each class. Then we just take the simple average of those values, so we sum them all up and then divide the total by 3. If we want to take the microaverage instead, we compute the same class-specific binary confusion matrices, but then rather than computing precision or recall from those separate matrices, we recombine them to form a single kind of super confusion matrix. In that matrix, we add together all of the true positives, all of the false positives, and all the false negatives. Then we compute precision or recall directly from that matrix. Now, an interesting quirk of micro-averaged precision and recall in a multi-class setting is that they'll be equal to one another, as you can see from the equations. Even more interestingly, they'll also be equal to accuracy. This only holds if you're micro-averaging across different confusion matrices generated from the same test results, like what you see here. In terms of what's better between micro and macro averaging, that depends on your individual classification scenario. Micro-average scores will be influenced more by class size, whereas macro-average scores take all classes into equal consideration. So if checking performance on all classes is equally important, macro-averaging is probably better. If performance on more frequent classes is more important, micro-averaging is probably better.